Ion exchange is an exchange of ions between two electrolytes or between an electrolyte solution and a complex. In most cases the term is used to denote the processes of purification, separation, and decontamination of aqueous and other ion-containing solutions with solid polymeric or mineralic ion exchanges. Typical ion exchanges are ion exchange resins, zeolites, montmorillonite, clay, and soil humus. Ion exchanges are either cation exchanges that exchange positively charged ions or anion exchanges that exchange negatively charged ions. There are also amphoteric exchanges that are able to exchange both cations and anions simultaneously. However, the simultaneous exchange of cations and anions can be more efficiently performed in mixed beds that contain a mixture of anion and cation exchange resins, or passing the treated solution through several different ion exchange materials. Ion exchanges can be unselective or have binding preferences for certain ions or classes of ions, depending on their chemical structure. This can be dependent on the size of the ions, their charge, or their structure. Typical examples of ions that can bind to ion exchanges are H+ and O, single-charged monatomic ions like Na+, K+, and Cl, double-charged monatomic ions like Ca2+ and Mg2+, polyatomic inorganic ions like SO42A and PO43A, organic bases, usually molecules containing the unfunctional group Nr2H+, organic acids, often molecules containing CuA functional groups, biomolecules that can be ionized, amino acids, peptides, proteins, etc. Along with absorption and adsorption, ion exchange is a form of sorption. Ion exchange is a reversible process and the ion exchanger can be regenerated or loaded with desirable ions by washing with an excess of these ions. Applications: ion exchange is widely used in the food and beverage, hydrometallurgical, metals finishing, chemical and petrochemical, pharmaceutical, sugar and sweeteners, ground and potable water, nuclear, softening and industrial water, semiconductor, power, and a host of other industries. Most typical example of application is preparation of high-purity water for power engineering, electronic and nuclear industries. That is, polymeric or mineralic insoluble ion exchanges are widely used for water softening, water purification, water decontamination, etc. Ion exchange is a method widely used in households to produce soft water. This is accomplished by exchanging calcium Ca2+ and magnesium Mg2+ cations against Na+ or H+ cations. Another application for ion exchange in domestic water treatment is the removal of nitrate and natural organic matter. Industrial and analytical ion exchange chromatography is another area to be mentioned. Ion exchange chromatography is a chromatographical method that is widely used for chemical analysis and separation of ions. For example, in biochemistry it is widely used to separate charged molecules such as proteins. An important area of the application is extraction and purification of biologically produced substances such as proteins and DNA/RNA. Ion exchange processes are used to separate and purify metals, including separating uranium from plutonium and other actinides, including thorium, and lanthanum, neodymium, ytterbium, samarium, lutetium, from each other and the other lanthanides. There are two series of rare earth metals, the lanthanides and the actinides, both of whose families all have very similar chemical and physical properties. Using methods developed by Frank Spedding in the 1940s, ion exchange used to be the only practical way to separate them in large quantities, until the advent of solvent extraction techniques that can be scaled up enormously. A very important case is the PUREX process, which is used to separate the plutonium and the uranium from the spent fuel products from a nuclear reactor, and to be able to dispose of the waste products. Then, the plutonium and uranium are available for making nuclear energy materials, such as new reactor fuel and nuclear weapons. The ion exchange process is also used to separate other sets of very similar chemical elements, such as zirconium and hafnium, which is also very important for the nuclear industry. Zirconium is practically transparent to free neutrons, used in building reactors, but hafnium is a very strong absorber of neutrons, used in reactor control rods. Ion exchanges are used in nuclear reprocessing and the treatment of radioactive waste. Ion exchange resins in the form of thin membranes are used in chloralkali process, fuel cells and vanadium redox batteries. Ion exchange can also be used to remove hardness from water by exchanging calcium and magnesium ions for sodium ions in an ion exchange column. Liquid phase ion exchange desalination has been demonstrated. In this technique, anions and cations in salt water are exchanged for carbonate anions and calcium cations respectively using electrophoresis. Calcium and carbonate ions then react to form calcium carbonate, which then precipitates leaving behind fresh water. The desalination occurs at ambient temperature and pressure and requires no membranes or solid ion exchangers. Theoretical energy efficiency of this method is on par with electrolysis and reverse osmosis. Other applications: in soil science, cation exchange capacity is the ion exchange capacity of soil for positively charged ions. Soils can be considered as natural weak cation exchangers. In pollution remediation and geotechnical engineering, ion exchange capacity determines the swelling capacity of swelling or expansive clays such as montmorillonite, which can be used to capture pollutants and charged ions. In planar waveguide manufacturing, ion exchange is used to create the guiding layer of higher index of refraction. Dealkalization, removal of alkali ions from a glass surface. Chemically strengthened glass, produced by exchanging K+ for Na+ in soda glass surfaces using KNO3 melts. See also, ion chromatography, ion, alkali anion exchange membrane, ion exchange resin, references. Friedrich G. Helfrich. Ion exchange. Correa-Dover Publications. ISBN A978-0-486-68784-1. Ion Exchanges, Walter de Guita, Berlin, 1991. C. Holland, Ion Exchange, Theory and Practice, The Royal Society of Chemistry, Cambridge, 1994. Ion Exchange, M. Decker, New York, 2000. A. A. Zagorodny, Ion Exchange Materials, Properties and Applications, Elsevier, Amsterdam, 2006. External links, Illustrated and Well-Defined Chemistry Lab Practical on Ion Exchange from Dartmouth College, Sommerplatz Illustrating Ion Exchange Processes, A Simple Explanation of Deionization, Ion Exchange, Biominewiki.